Okay, good morning everybody. We are starting our new chapter number 3, memory management. So as we said before, operating systems are good for two things. One of them is the resource management. CPU is a resource. Memory is a resource. Secondary storage, our disks, our input-output devices are resources, so we need to manage them. And the second thing is that we need to abstract away the details of the complicated hardware. CPU is a complicated hardware. We use the idea of processes to make it easy for the user to write programs for the operating system. Processes and the threads. Of course, we need to solve a number of problems, and we talked about them. So far we talked about managing the CPU and making the details of the CPU hidden from the user in chapter number 2. So we are going to do the same thing with the memory now, because maybe this is a wrong thing to say, but the most important thing in our computer is our CPU. That's why the CPU is chapter number 2, abstracting away the details of CPU and managing the CPU. And then the second thing is our memory. So we are going to look at the memory, and most of the solutions that are developed for making the memory more manageable, making the memory more accessible for us, is affected from the CPU abstraction. That's why the CPU has to come earlier than the memory. But again, we are going to go back and forth between talking about memory and the CPU a lot. Most of the decisions that we make in this chapter will be based on our decisions that we made about the processes and the threads. Okay, and it is likewise actually. Remember, I mostly talked about when I talk about something, for example, context switching. I told you that, well, context switching is expensive because we need to save these registers, but it is more expensive. It is expensive because there are lots of things to do about the memory, and that will come to our discussion this week or next week. Okay, so memory management. Memory is expensive, especially our primary memory, core memory, but it keeps getting larger and larger. Nowadays, our home computer has hundreds of thousands of times more memory than the original supercomputer of the day. For example, in 1960s, we have these series IBM 7090s. It used to cost $20 million. Well, it didn't cost that much then, but our inflation-adjusted value is $20 million. And their memory, this computer's memory is not more than 100,000, 1/150,000 of our current computer. It's just 32 kilobytes, if you like to say it, or whatever the word size is. So, but it was $20 million in those days, okay? And this was a computer. So you need lots of people, as you see the tape drives, okay? So who is going to load all those tapes? Okay, these operators are responsible from them, and there must be some. Yeah, this is the printer. See, this is producing the printer output, and there must be a device that reads the punch cards somewhere. I don't know. So it's an expensive computer, but its memory is only this much, 32 Ks. Okay. So nowadays we are talking about gigabytes of memory, tens of gigabytes of memory on our computers, and the memory is still not enough. It will never be enough. As this saying goes, programs expand to fill the memory available to hold them. Okay, so that's why we need to manage the memory very carefully, like we did with the CPU. Okay, so the main memory is resource is a very important resource. We have to manage it, okay? And we have to be very careful about it. Because we have to we have to abstract away details of it. And you might say that what is so difficult about managing the memory? I mean, memory is something like that, okay? Address number 0 and address number large number FF, okay? That's all memory. And put your operating system here and put your program number there and put your program number 2 there, and that's it. Why is it so complicated? Let's look at some of the problems, okay? In the early days, actually, it was like that, okay? In the early days, it was like that. In old mainframes in 1960s, this was the case with the batch processing operating systems. Your operating system sits at the bottom of the memory. It is in the RAM. And you put your user program, a single user program, on top of it. Whenever this program is done, okay, the operator changes this program with a new one, and that one runs, and it goes that way. So the early version of the operating systems were like this. Certainly you didn't have any need for managing the memory. Memory is managed by the program itself. The same thing is valid for the CPU too. Whoever runs this program, he or she owns the whole computer, including the CPU and the memory. They can do whatever they want with the computer. Okay? So there was nothing to manage much, but lots of things missing in this case. There is no protection, there is no multitasking, there is no time sharing, and etc. The problem becomes when you have those kind of features. When you have those kind of features, this picture is not sufficient anymore. You need to do more. Well, some people said that maybe we don't change the operating system much. Let's put the operating system in read-only memory, ROM, instead of RAM. Let's put it in ROM. And in that case, the user program cannot accidentally or intentionally change the values inside the operating system. Okay, so that might be one solution to some of the problems of this user program messing up the operating system. But operating system has to modify some memory, so operating system has to have its own memory, and it has to use this memory inside this RAM, like there, okay, and this is already accessible to this user program. And some other solutions were, nowadays we are currently still using some version of it. For the early MS-DOS systems, you say that, okay, operating system can change from time to time, we upgrade them, don't put them into our ROM. But device drivers, the keyboard will stay the same. Why do we put the device driver in the RAM and this kind of solution? Again, these solutions, they assume no memory abstraction. Okay, they say that memory is yours. As an operating system, I am not going to help you. I am not going to help you about your memory management. Do whatever you want with your memory. Okay, so of course we are not doing this anymore. And let's look at this picture now. Let's try to do multitasking, okay? More than one program at the same time in our memory. Let's say this is our very simple computer. It has only 16 kilobytes of memory. And I am running this program. The first address that I am going to execute is this address number 0. Jump to address number 24. And the 24 says that move something to something, then add something to something. It goes that way. So this program A, is running nicely. Or alternatively, I can do program B. And program B says that at the beginning, jump 28. Jump 28 compares something to something, and it runs. Let's say I like to run these two programs simultaneously. Well, you mean what I mean simultaneously? By time sharing. by multitasking. Okay, so I need to load both of them. I need to load both of them in my memory at the same time. So this is what I'm of course you need larger memory. Let's say I have larger memory, 32 kilobytes of memory. So I loaded program A here and program B here. So this is A and this is B. For A, life is the same as before. Jump 24 and the address number 24 is here. It goes there. But for program B, the first instruction is jump 28 because that was the original program, right? But the address 28 belongs to this program A, and in fact what I mean is jump to this address. Okay, so it is not as easy as for the multitasking. It is not as easy as putting the program somewhere in the memory and letting them use the CPU. It doesn't work that way. Well, in this case, it looks like we need to have some kind of a way of changing these numbers, changing these addresses, and we will see a number of solutions, and we will like some of them and we won't like some of them, as you know, like we did for the CPUs, and we are going to discuss them, and later we will tell you what the current our modern computers do to solve these kind of problems. The first solution might be, why don't operating system knows that I am going to load this program at this address 16384. Okay, operating system knows that. So why don't I change all the absolute addresses inside this program? If it says jump 28, then I would add this number 28 and change it to jump 16412, right? So I am dynamically, when I am loading this program B, I am changing all these kind of absolute addresses, like these kind of jump instructions or function calls and etc. So that's called static relocation. Okay, at program load time, who is loading the program? Our operating system. At program load time, the execution address I know, and I would add the actual offset to the presumed location by the compiler and the linker. The compiler and the linker say that, okay, inside this program, this needs to be changed, okay, this needs to be changed, and wherever there is a jump instruction, return the function call instruction, these kind of absolute memory reference instructions, okay. So compiler and the linker marks those for us, and okay, during the program loading, I change those values one by one by adding the program starting address. Okay, so that means that at the beginning of the program execution, when the program is loaded, okay, you need to change all of them. So the operating system has to work with the compilers and the linkers and has to do that. It kind of solves this problem, right? I mean, this program will work fine. This program will work fine because for this one I will add 0 to this number 24 and it will work. For this one I will add this number to this number, the jump, it will work. The only downside is I need to make this static relocation every time I load my program. And then we talk about the problem, right? What is the problem with this approach? Well, it takes some time to make those decisions. That's one thing. And the compiler and the linker has to help me. So, I mean, I need to use special compilers and the linkers to give me that information. That's the second thing. Well, maybe I can live with that, but there is something more. There is something more important than those. Operating system is helping me to use memory between many programs. So that's good. But I am missing something here. I mean, even if I do this static relocation, I won't be able to provide, yes.
First program can jump the second one.
Yeah, the first program, if the first program says by accident or by intention, jump to somewhere. Or the first program says that I am going to modify this address of inside the memory. There is nothing prevents it from happening, right? So there is no protection. Well, one of the tasks of the operating system is to provide protection. That's the managing the memory. This one doesn't provide any protection, and that's why we don't like this much. But it was used before by the early computers. People later gave up, and they found much nicer, much more elegant solution than this. Okay, so that's called static relocation. People said that you can't let this happen. You cannot let this program A modify any part of the main memory. We need to restrict this. So they have invented this idea of address spaces. Okay, address spaces. The address space kind of, I mean, the idea of address space to the memory corresponds to the idea of the processes and the threads to the CPU. Okay, address space is a set of addresses that a program can use. So you will say, okay, as an operating system, as the hardware, maybe if I have more than one program loaded in my computer's memory, OS, program A and program B. Okay, this is address 000. This is address F. Okay, you would tell this program A that your address space is between here and there. Okay, this is your address space, and you can't access anywhere else other than between these two. For program B, you say that your address space is here between these two. Okay, this is for A, this is for B. And operating system and hardware make sure that anything outside of this limit is not accessible. Yes?
In static relocation, can't we just say there is a limit that we can jump from the other address spaces?
Well, I mean, you don't have any. Once you do this, okay, you let the program run. How are you going to tell that you cannot access anything about that?
I mean, process table maybe should hold the limit number, maybe limit address number.
Yeah, if you say that, okay, you are the process, you are not going to access anything larger than this number, if you say.
Yes.
So what happens if the process A says that I don't care?
Why it says I don't care?
Because it's a badly written program,
Okay.
or by accident, it has ill intentions. This one will say, I am going to do whatever I want. I don't care if you are the operating system. Well, that's what happens, right? Okay, so protection has to be provided for all the programs that are either, I mean, didn't you write any C program that crashed? Why did you write it? It is not our intention to write crashing programs, right? It just crashes because dealing with the pointers and the dynamic memory is not that easy, so it crashes. Okay, if a crashing program tries to access lots of nonsense locations, and if we let them do that, that's going to hurt other programs, and that's going to hurt the worst thing is that's going to hurt our operating system too. Okay. So, but we will come to that idea later. But we will need help from the hardware. Okay. We will talk about that. Okay. So the idea of the address space is this. So we are going to limit each process, saying that between this and this, that's the place that you have. You cannot access anywhere else. What if they wanted to access anywhere else other than the address space? The first thing is they can't. There is no way. Even they can, the hardware will stop them, saying that they will tell that operating system told me that this is the address space for you. There is no way you can access them. You can access out of this address space. Okay. So each process has its own address space. Here we say process, not the thread, because threads, they share address spaces, right? That's the most important, one of the most important differences from the processes. Each thread, the threads of the same process shares the address spaces. Okay, so each process has its own address space, independent of those belonging to other processes. And the nice thing is that each process thinks that they start from address number 0 to some large address. So they don't care where they are in the main memory, actually. Okay, no relocation is needed. But for that, you need the help from the hardware. Hardware needs the help. Without the hardware help, we cannot expect the regular programs to obey all those rules, even if they have written nicely. Accidents can happen. Okay, so this is important. Just as the process concept creates the kind of abstract CPU, okay, the address space creates the kind of abstract memory for the programs to live in. Okay, we designed this idea of the processes, and we built everything on top of the idea of the processes that abstracted away the details of the CPU for us. Now we are going to do the same thing with the memory. This time we will keep using this term address space. Okay, so the modern computing is based on processes and the address space. Okay, so let's look at how we can get help from the hardware to provide this address space. CPU says that I am going to give you this. Okay, for each process there will be a base and limit register. Okay, there will be a base and limit register like that. As an operating system, I decided that this program will be loaded at this address 16.384. And as an operating system, I know that the size of this program is this much, 16 Ks. Okay, and as an operating system, I also know that this program is loaded at address 0, and size of it is 16K, kind of 16, yeah, the same size. Okay, and I am telling this to the hardware, and hardware does this. Okay, whenever I see a absolute addressing like jump 28, okay, the hardware dynamically adds this value to this one, and it goes to the desired location. So this adding thing is done dynamically during my program's run, okay, but the program is not changed at all. Okay, the program runs like I am loaded at the bottom of the memory at address number 0, and it goes like that. So I get help from the hardware every time I make a memory reference. Okay, I add this number to that memory reference, absolute memory reference, and I get the desired address. This is called dynamic relocation. Why is it dynamic? Because this addition is done during the runtime, okay, and the contents of the base register is added to all memory references, or to all absolute memory references, of course, absolute. Because sometimes you will say that jump 10 addresses before me, or jump 10 addresses after me, and etc. Right? So those are relative addresses. We are talking about the absolute addresses. Okay? And the other nice thing is that, of course, I cannot say jump -2, right? and that's not allowed. There are no minuses. I would say a value, but if the value is too high, too large, it is larger than the limit register, then the hardware says that no, this is not going to happen, because this is way beyond your limit, memory limit. I will stop you from doing this. Okay, so this is the solution for base and limit registers. So we kind of we kind of made this idea of the address space available to the processes. Each process would think that they have, starting from address 0 to some limit register, they have the whole space. They can do whatever they want inside their address space, and all I need is the hardware hub to provide me these two registers. Of course, these registers will be different for each process, and I will keep them in my process table. Okay, whenever I switch between processes, I load these two registers to my CPU, like the stack pointer or the register AB, etc. These are two special registers, and hardware knows what to do with these registers. And the nice thing is this is our CPU, right? This is our memory. Of course, these are connected through the bus. Remember, there was a circuitry inside my CPU. It was called MMU, memory control unit. Okay, memory controller unit. This MMU is responsible for translating those addresses from the address space address to physical memory addresses. So the MMU is going to do that. Okay. So at every instruction, I need to provide this hub as the hardware. Okay, good. That's dynamic relocation and limit register. Okay. So if I am outside of this limit, again, hardware causes a trap. Hardware causes an interrupt, and who's going to handle the interrupt? Operating system. So nobody's allowed to reach outside. So we kind of solved this problem of static relocation. Now more than one program can live in my memory, but as always, we will have a problem about this too. Okay, so that's going to be expensive, because each memory reference is going to be an addition and comparison. Okay, an addition is expensive because, I mean, if you add these binary numbers, okay, you know that, right? 1 1 0, and there is a carry bit, and this is 1 1, again 0 1 0 1. There is a carry bit, and you need to do it in sequence, and it takes time. It is not like a comparison. With the comparison, you can do the comparison at the same time, all bits to the bits, but with the addition, it is expensive, so we don't like this much. Okay, that's one thing. And you might say that let's make a more complicated CPU and handle this. Yeah, that's okay, but there are other problems. Okay, the problem is this. Remember, I showed you my programs process table, right? There are more than 100 programs trying to run at the same time. There is no way that I can fit all of my programs to my memory at the same time. This is trying to do the similar stuff. It is trying to say that this program is loaded in my memory, and this program is loaded in my memory, and I am going to load all the programs that needs to be in my memory. I am going to run it this way. That's the idea, but that doesn't work, because no way that you are going to fit all of your programs in your memory at the same time. Okay, so programs are too large, they do not fit into memory. We need to find a way of doing it. Simple solution is swapping. Okay, simple solution is swapping. So this is what we are going to do. Okay, let's say my program A is running, okay, operating system at the bottom. I am using the base and limit registers. And then I decided to load another program B, okay, and that program started running too. That's good because I have enough memory. Then I have my program C. It started running using this round robin scheduling maybe. Then I need to load another program D. But for D there is no space, so what am I gonna do? I need to make a decision. Should I remove program A or B or C from the memory? I decided that A will be unloaded from the memory. So I write A to disk and load D from the disk. Now D is running. Then my scheduler decided that A will be loaded back. So I need to remove somebody. B is removed and A is loaded. As you see, I am swapping back and forth between the disk and the main memory, depending on my scheduling decisions. Because I have 4 processes, A, B, C, D, I don't have enough space to fit them. Enough space to fit them in my memory at the same time. I need to do the swapping all the time. Okay, so that's called swapping, and swapping is an unavoidable part of operating system's life, and we don't like swapping. Swapping is more time consuming, much more time consuming than the context switch. Okay, and unfortunately, when you do the context switch, from time to time you need to do swapping, and once you do your swapping a lot, okay, that will be a real trouble for you, because multitasking is going to be too expensive to keep it in your system. So we don't like swapping. It is unavoidable. If it is done only a limited number of times, it is okay. But if I keep doing this, every time I do a context switch, I am going to spend most of my time doing the swapping instead of running my programs. So we will come to this, and we will try to see what we can do about swapping at the end of this chapter. Okay, so let's look at the swapping in more general. We don't like swapping, but that's why we need to know it. Physical memory is not large enough to hold all the programs, so swapping, the definition is this. Okay, write the entire program to the disk when it is blocked, and read it back again when it is time to run that program again. Okay, and so apparently this writing the programs back to the disk frees up memory, but this kind of consumes memory bandwidth. Okay, and it makes our CPU wait a lot for this swapping to occur. But again, without the swapping, I cannot fit enough number of processes to my computer. I have to do that. So this base and limit register solution has this problem of swapping. It makes the swapping even more serious, and we need to find a solution for that, and we are going to see our solution kind of solve that problem. Okay, so are there spaces, and we are looking at that idea. Base and limit registers kind of solve that problem of the address spaces. With the help of the swapping, we kind of have a solution to a multitask system. The problem is this: the size of the program is something critical. I mean, how much memory I should allocate for a process is a critical decision. Why? Because if I allocate too much space, then that's going to occupy lots of memory space, and that will cause lots of swapping. If it is little, then my program will not work. Okay, usually I do it this way. Okay, let's say I have program A and program B. The code part of program A, the code segment, that is the running the instructions itself. Of course, I need to load them to my memory. I need to load them to my memory. Yeah, that's true. But I need also space for stack and the heap, like this one. Okay. This is my program A, and this is my stack. And whenever I use stack, I push values on it, and stack grows downwards. And this is my heap, and heap has to grow and shrink too. Okay. So I need to make this decision, and I will say that for this program A, I need this much space, and I know that this part of it will belong to, okay, will be currently empty, and I will not use it at the beginning of the program, but later it could be used. So I need to make that decision too. As an operating system, okay, as an operating system, I will make that decision. The program size on my memory is not the same as the program size on the disk, because on the disk you don't need memory, right? On the disk you don't have any modifiable memory. On the disk you have you store only the instructions and your fixed data for that program. When the program runs, you need the instructions, you need the fixed data, also you need the data for changing the values. So more space will be allocated for each program. So that brings the question of how do I keep this information? I mean, as an operating system, I am responsible for managing the memory. Yeah, that's true. How do I keep this? How do I keep this information in my memory is something that needs to be decided. What's going on? Didn't I erase it? Patience and clear. Yeah, okay. Okay, because I mean, how do I know that? How do I know that this part of the memory belongs to program A, and this part of the memory belongs to program B, and this part of the memory is free? Okay, I need to keep this information. So there are basically two ways of doing it. One is called the bitmap approach. The other one is the free list. Okay. So when the memory is assigned dynamically, the operating system uses these two data structures, bitmaps and the free list, and this is how it is done. First of all, for each of these approaches, I use a predetermined block size. Okay, let's say this is my whole memory. Okay, and I say that my block size will be 4 kilobytes, and I allocated 1, 2, 3, 4, 5 blocks for process A. Okay, 1, 2, 3, 4, 5 blocks for process A, and that means process A will take 20 kilobytes. Okay, and there is a free block, 3 of them, 3 blocks. Okay, 12 kilobytes. Process B, 1, 2, 3, 4, 5, 6, 24 kilobytes, and C, okay, it is 12 kilobytes. Is that, no, 16 kilobytes? It goes that way. Okay, so this 4 kilobytes is a system-wide value. Operating system says that, okay, my block size is, memory block size is 4 kilobytes. Okay, and if I have, let's say, 400, or maybe I should do it this way. So the 4 kilobytes is 4 times 2 to the power 10. Okay, so we like using the binary and the exponential values in computer science, as you know, okay? And let's say my memory is just 2 to the 20. Okay? So I have 1 megabyte of memory. Okay? So how many blocks do I have? I have how many blocks do I have in this system? If my block size is 2 to the 4 times 2 to the 10, or this is equal to, of course, 2 to the 12. Okay, if this is my block size, if this is my memory, how many blocks do I have in my memory? What? If this is my block size, if this is the size of my memory, it is, you divide it, right? 2 to the 20 over, if you divide this number by this number, you get 2 to the 8, right? You just subtract it. 2 to the 8, okay? So I have 256 blocks available in my memory. So this bitmap approach says that keep a table like this. Inside this table, you have 256 binary values, zeros and ones. This one represents the availability of the first block. This one is the second block, third block, fourth block. It goes that way. So I have a special place in my kernel in my operating system. It's a bitmap field, okay? It has 256 binary values. If there is a 0 in there, the corresponding position in my memory is available. It is free. If it is 1, then it is used. Okay? So the operating system with this approach, the operating system keeps track of the memory using this bitmap. Okay? So whenever I need to run a program, operating system scans this table and it says that, okay, I found 3 blocks free somewhere. I can use this place to load this program. Okay, so that's called the bitmap approach. That's called the bitmap approach. And obviously, this is a very simple idea. And if it works, we like the simple ideas in operating systems or any field of the computer science and engineering. Okay, if it works and if it is simple, that's good, because when you load a program, you need to be quick, and you can't afford to run very complicated algorithms. So all you do is you search this table and you found your space and you allocate it. When the program ends, you just convert those ones to zeros, so that we know that those are all available. So that's called the bitmap approach. Okay, that's called the bitmap approach. The alternative is the linked list approach. That's the linked list, the second one, or the free list, linked list. This free list does this. Okay, it says that I have a linked list of memory chunks. It says that starting from block number 0, length of 5. Okay, block number 0 for the length of 5. It is held by a process. That's my first node. And after that, starting from block number 5, for the length of 3, there is a hole, so this is available. Again, after that, I have a process holding up memory starting at address number 8, and for a length of 6 blocks. Okay, so that's called the free list or the linked list approach, and it works this way. So which one would you prefer? Do you see the advantages and disadvantages each one of them? Well, I mean, this is very simple. I like it, but this one is, let's assume that I don't have many processes in my memory. Okay, so this linked list will be very, very short, right? So that's all I need to keep. That's all I need to keep. But for this one, doesn't matter if you have a 0 process or 12 processes or 100 processes, you have to keep the same amount of memory for your bitmap representation, right? So if your memory is full, you will have lots of zeros in this table, but this linked list will be very, very short, just 1 or 2 nodes. But this one starts becoming more helpful when you have lots of processes in your memory. This linked list will grow and grow, right? The size of this table will stay the same. Okay, so kind of make the comparison between them. You might say that, okay, what is wrong with keeping 256 bits? Okay, I mean 256 bits is a very, very small value to keep. Yeah, that's true. That's true, but these are not very realistic numbers, actually. I mean, your block sizes are realistic, but nobody has 2 to the 21 megabyte of memory anymore. Okay, nowadays we have memory sizes starting from gigabytes, right? 2 to the 30. So it becomes 12, 18, right? 2 to the 18, and 2 to the 18 is a lot of binary numbers. Okay, so this will get much larger than this one. Good. Any questions so far? Any questions? Did everybody sign the attendance sheet? Okay, so let's take 15 minutes of break. After the break, we will continue. Before you leave, open the windows, please. Open the windows.
İki tanesi var herhalde Instagram.
Yapma ya.
Evet, 2 sayfa aynı.
İsmi olmayanlar var mı peki? Arkadaşlar siz nereden çıktınız ya? Gezi yoklama. Geç mi geldiniz?
Evet, geç.
Numarası. Ama birkaç tane var. Hayır. Derse geldin mi?
Şimdi.
Derse gelmediysen niye imza atıyorsun ki? Ha? derse gelecek baktık işte.
That's what she said. Oh, that's a piece of practice. Abi ödev var mı? Ödev vereceğim de 5 ödev var. 3 günlükte. Şimdi 3 tane sınav sorusu var.
Gerek var mı?
Ya kötü ya. Ne kötü? Batalım
Arkadaşlar o savaşladınız mı?
Ne?
O savaşladınız
Bu adamlar dağdan bir şey yapmış geldi benim kulağıma.
Hayır denedim. Bir günüm verdim. Sıfırlar. Ya bir şeyler yaptım. Başka bir sürü şey bozuldu. Ben de bıraktım yani.
Şey mi? Adamın kolu mu bozuldu?
Şeyi sildim yani. Proses silmeyi yaptım. Sonra da bozuldu yani. Kafayı yemeye başladı. Uğraştıkça daha çok bozuldu. Ben de saldım.
Yok mu ödevi yapmak isteyen?
Hocaya da yazdım dediler zaten. Dedim bir PS falan yapın bari.
Onu da dün gibi düşünüyorum.
Yapar herhalde sana. Ben de yazayım sana. Okudum kanka.
Çocuğun beni yapması için. Bir dakika bir yazmış. Piyasa da söyledi. Beni atmayıp Teams'ten yazın diye 50 kere söyledi. Ben Teams'ten yazdım.
Ben de bilmiyordum abi. Niye mi yaptın? Abi biz herkes ne kullanıyor? Yanlış anlayamıyorum. Yemek
Bir şey biraz anladın mı?
ama gördüğüm çalıştık. Allah alırız biraz.
Kimse yapmazsa bence kan değişmez.
Aynen.
Bir şey yapıyoruz.
Yani ilerleyenler var. Hiçbir şey unutmuyorum. İlerleyenler var. Şu piyasayı değil mi sen? Kanka. Piyasada bir şey var mı?
Birisinin görüntüsünü de var ama bir de sen ben oturuyorum.
Sen mi yapacaksın?
Sen birazcık biz onu da
Şöyle bir tane multitasking diye multitasking diye konu var. O interrupt noktası diye bir şey oluyor. Interrupt noktası de interrupt stop noktası yaşıyorsun. Yani SMS'de bir şey yok. Oraya kadar takip edebildim onu. SMS'ye gelince anlamadığım için sonra oradan oraya gidiyor.
Register'ların son durumun şeyini oraya koymuş.
CPS mesela kontekst.
Kontekst.
Bir de sen birazcık
Sürekli böyle kaynatıyor, yakıtlıyor. Sonra silince geri eski CPU'de de yani. Bir kere oluyor. Sonra tekrar yeni yapmaya çalışıyor.
biz neyi kullanıyoruz? Bir tane sıkı bir olsun var zaten.
Bu ders bir şey var.
Benim aklımda bir şey var. Bence diğer kodları değiştirmek.
İçine internet yapalım.
Desen falan yazıyor.
Evet,
Sport
ben
yazdım var.
bu
Aynen.
kalkıyor.
Kontekst daha acil belirlerine baktım.
Hiç alakası yok bu arada. Kanka ne yaptınız?
Biraz başladık ya. Abi kolay alalım zaman. Kolay. Videoları iyiyiz ya. Biraz da böyle biraz böyle gidelim abi. Sadece izlemekle kalmıyor videolar.
Aynı boyut olduğu için
O adam izliyor işte. O YouTube'daki adam izliyor. Ama YouTube'daki adam
Ne kadar ilerledin?
Ne? Ha.
Ne kadar ilerledin? Ne yaptın?
İzledim hocayı da.
Ha videoyu.
Hayır videoları da izledim üstüne de yaptım bir şeyler.
Ne yaptın?
böyle hiçbir şey yapamıyorlar.
Progressive Consumer yaptım.
Tamam.
Peterson Solution falan. Trade yaptım. Trade Yield yaptım. Terminate'le oğlum benim sizin kadar sizin işiniz çok da benim iş çok da gerçi bende şey yok, sistem falan yok.
25. video sekreter oluyor mu? Yoksa yazdığı yerleri falan görüyor mu?
Sana tavsiye edeceğim biraz yerlerde bakmam. Çünkü
Şimdi bir sıra yapacağım orada.
Context switch'i nasıl gerçekten anlamak için Kendi context switch SMBC'yi falan yazdım da direkt interaktım böyle. İnteraktifin yaptığı kodları direkt çekmiştim. Biraz basic yaptım. Ama yani olayı anlamak için
Başka var mı geldi? Ne kadar da
yavaş yavaş ilerledim. Mesela baktım mesela bir saat falan. Sonra açıyorum. Zaman bilimler bakıyorum. Böyle sonra tekrar
Okay, so these are the two I need to be Okay, so these are the two main methods of keeping your memory usage. bitmaps and free lists. And as we said before, both of them has advantages and disadvantages. Bitmaps is for both of them. Memory is divided into allocation units or blocks. Okay, and what did we say? Let's say we have our block size is 4 kilobytes. How did I make that decision? I don't know. I just made this decision by looking at whatever was done before. Usually we have 4 kilobytes, 8 kilobytes, 16 kilobytes of block sizes, and sometimes this is configurable. You can configure this with your operating system. Usually the numbers are 2 to the 10 or 2 to the 12 or 2 to the 13 and etc. So that's a design issue. So let me ask you, what is wrong with a block size of 2 to the power, let's say 0? Let's say our block size is just 1 byte versus a block size of 2 to the 20, 1 megabyte. Well, we don't like the small numbers much, we don't like the large numbers much, but what is wrong with the small numbers and what is wrong with the large numbers? Instead of 4 kilobytes, if I make my block size just 1 byte, what would be the problem?
You need bitmap as much as your RAM.
My bitmap size will be very, very large, right? If my block size is just 1 byte, my bitmap will be as large as my memory or rate, right? Because each one will point to a 1 byte, each one will point to a bit. Okay, so that's not a good thing. Yes. Yes.
Your microphone is muted in Teams, they say.
Where did it go? Here it is. This one. Can I grab it? Yeah, okay. So the smaller values means that the larger bitmap table, right? That's the smaller numbers, smaller block size. What about the larger block sizes? For example, if my block size is instead of 4 gigabytes, just 1 megabyte, okay? I have 1 megabyte block sizes. That will be good for the bitmap table, right? My bitmap table will be much smaller, but the problem would be what?
Not used memory.
Not use memory. What do you mean?
A process, let's say a process needs just 10 kilobytes.
Yeah.
We are giving him a 1 megabyte.
Let's say my process D is using, let's say my process E is just using, let's say it needs just 20 kilobytes, right? Okay, but since my block size is 1 megabyte, I need to give this E 1 block. That's the minimum I can give. So 1 megabyte minus 20 kilobytes will be wasted, right? So the larger block size means that unused memory inside my allocated blocks. Smaller block sizes mean that my bitmap table will grow larger. So I need to find a trade-off. I need to find a balance. Okay, that's one thing. The other thing is, okay, I need to make a search on this table. I mean, let's say if this is my table, and I have a new process new process needs 20 kilobytes of space. I need to make a search on this table, right? So if the table is large, making this search is going to be difficult. It's going to take a lot of time. Okay, with the linked list. Okay, with the linked list, if you follow the approach of the linked list, some of these problems go away, but Let's look at this problem. Let's say I have three processes, A, X, and B. X terminates, I have this one. Okay? And then if I have this, when X terminates, I have this one. I'm trying to get to some point, okay? Sometimes when this X terminates, I need to merge these two, okay? I need to merge these two, and this time I need to merge these three. Remember how the linked list kept? Okay? Process whole process, okay? If this one is terminated, then I need to merge this whole with this one. And if in this case this one is terminated, then this one and this one. If both of them are terminated, then I need to merge these four. So I need to find this who is going to merge with who is going to be an issue for the linked list approach. So both of them has their own problems and their advantages. So the thing that comes to mind is, how are we going to find the place to put our new process in my memory? Okay, so people have suggested many ways of doing it. If this is the case, okay, if this is the case, let's say again, let's say I have a new process, process G. It needs 15 kilobytes of memory space. Okay, how do I decide that? How do I decide that which place is good for this one? Okay, also how do I make a decision if two places are available, which one to pick? So obviously I'm going to look at this position, and this position, see which one fits. I cannot put a process into a position where there is not enough space. Space should be equal to or larger than the process itself. So how am I gonna do this? The approaches are this: first fit, next fit, best fit, worst fit, and quick fit. Okay, so let's look at these approaches, how they are doing it. The first fit is this. Okay, you traverse the list, you walk the list until a large enough chunk block is found. You check all the blocks one by one. You say that, okay, I found a place, I can fit it in there, I don't care about how large it is, okay, so I use that place. Okay, so it's very fast. It just uses the first place available. So if you are doing the linked list approach, let's say I need a process G. Process G needs 8 kilobytes. That means it is 2 blocks, right? 2 blocks. So this is a whole. This is a process not available. The whole, it says that 3 blocks are available. 2 is enough for me, so I get this one. I immediately take that one. That's the first fit approach. Okay, and do the same thing with the bitmap approach too. So you have to scan the bits one by one, and you say that, okay, these 3 bits are available. Each one is 4 kilobytes. That means that it is larger than 8 kilobytes. I'm going to use that one. That's called the first fit. Okay, first fit approach. Okay, and allocate as much of it as needed, because in that case I had 3 blocks available, but I needed 2. So I'm going to use 2 blocks, and one of them will be marked as unused, and I would return the unused one to the free list. Okay, and whenever you free memory, you just merge the adjacent blocks, and that will be okay. So that will be the first fit approach. So it is very greedy. It just finds the first place the first place that is large enough to get my process. Okay. So the next fit approach is the same as the first fit, but every time it needs to make a search, it doesn't start from the beginning. It starts from where you left off. Okay, so the next search starts from the result of the previous search. So if the first fit is always starts from the beginning, so you keep using the beginnings of your memory more than the other places, that might cause some problems. So to prevent those problems, there is this approach of next fit. Okay, so the starting address of your memory changes every time you make a search. That's called the next fit approach. Okay, good. Some people say that first fit or next fit is not a good idea, because let's say this place is there is a process, there is a very large chunk of memory available, there is another process, so this is whole. Let's say this whole is 32 blocks. I have a new process, P2, it needs just 2 blocks. Okay, so this one takes this 32 block space available and puts P2 in there and makes this whole 30, makes it smaller. Okay, so next time when a process needs 32 blocks of contiguous space, I won't be able to find it because this P2 uses it. Some people say that maybe this is not a good idea. Maybe I should keep searching to find the best place. Okay, so the first fit seems wasteful. So let's continue our search and find the best fit that has the closest match to our memory requirement, that is larger than or equal to our process size. Okay, so find the free block that is closest in size to the request. Okay, and that will be our algorithm. And if I am using a linked list approach, if I am using the linked list approach like this one, if I keep this linked list in the available whole list order, for example, the largest whole is at the beginning, and then the smaller whole, etc., with respect to the whole size, then doing the best fit is not a very big problem, because you make a simple search from largest to the smallest, and once you find it, then you will use it. That's called the best fit approach. Okay, best fit approach. Okay, and it looks like best fit isn't more efficient than the first fit, because what is the problem with best fit? Remember I told you about the problem with the first fit? It just makes this available large chunk of memory smaller and smaller and smaller. Okay, so whenever I need a large memory, maybe that will not be available. Best fit will not do that. Okay, best fit will not let you use this large chunk of memory for small processes, because it makes you use small places. But best fit is not going to solve this problem, but it creates other problems. It causes a very serious problem, actually. Yes?
If there is no exact fit, it will search for whole list.
If there is more exact fit?
No exact fit.
Yeah.
It will search the whole list.
Exactly, yeah. If this is my memory, there is a process in here, and there is a hole in here. There is a process and there is a hole. Okay. Let's say this hole is just 3 blocks and this hole is just 4 blocks, right? If I need memory for 2 blocks, okay? So this best fit is going to choose this one. Why? Because 3 is a better fit. It will use this part of it, and this one will be a hole. Okay? So I am creating a hole of 1 block size, which is not going to be very helpful for me. Why? Because I mean, you don't find many processes that need only 1 block, right? That's a very small thing. So the best fit creates lots of unused small memory segments around. Okay, that's called fragmentation. Fragmentation, or this is called external fragmentation. External fragmentation is the configuration of the memory where you have lots of small unused places in your memory and nobody can use them because they are very, very small for a regular process. External fragmentation. So the best fit tends to create this external fragmentation. You may ask, what is internal fragmentation? Then internal fragmentation, remember my extreme example of one block is just 2 to the 20 bytes, right? And if my process just needs just 4 kilobytes, so rest of this block will be unused, right? This is called internal fragmentation. So inside your block, you have lots of unused spaces. That's called internal fragmentation. Both of them are bad. Both of them are bad. Okay. So this external fragmentation is caused by your block size, your memory fit algorithms, and etc. Okay. So there is no way to prevent external fragmentation altogether with these kind of approaches. But I'm going to give you one perfect algorithm that eliminates the external fragmentation altogether. Internal fragmentation will stay. But it is a completely different approach. And most modern operating system uses that one. By the way, it's going to be funny, but you are used to funny things in operating systems world. None of these techniques are used anymore. These are kind of educational, maybe I would say, algorithms, just to teach you what kind of problems we need to solve. And I'm going to give you one algorithm that's going to solve most of these problems. Okay. But people have worked on these problems a lot. That's why we have these algorithms. So best fit causes more wasted memory in the case of external fragmentation. Okay, and some people are smart. How about the worst fit? Okay, worst fit, as the name implies, find the largest one. Okay, largest memory block available, and use it. This one should cause less fragmentation. Okay, and it turns out that the first fit and best fit are better than, and they are pretty close. So the first one that we looked at, the first fit and the best fit. Okay, how did they know that? They run simulations. Okay, they run simulation. What's a simulation? It's like your homework, right? Your operating system, your hardware, everybody is in software actually. You can do whatever you want. You are running many programs, okay, regular programs on your simulated environment, and you see how much of the memory is not used, how much of the memory is fragmented, how much there is external fragmentation, and you know how much time you spend for searching for the available memory, right? So that's the simulation. The simulations show that, okay, first fit and the next fit, okay, are good ones. And worst fit is not being not that good, okay. But okay, when you keep using first fit, this is the inefficiency of your algorithm. It is 1/3 of your memory may be unusable. How come it is not usable? It is unusable because of the fragmentation, external fragmentation. You have this your bitmap. This is your bitmap, okay. You have lots of processes, process, and process, okay. These spaces between the processes are available, but they cannot be used because no process is small enough to fit into those locations because of the fragmentation. Okay, how would you solve this problem? You might say that, okay, let's move the processes around. From time to time, operating system says that, okay, I have too much fragmentation. I need to compact my memory. So how do I do that? I stop all the processes. I move my P1, P2, P3, P4. P1 is going to be there, P2 is here, P3 and P4. And remember these three blocks, they will be end of here, okay? So I merge them together, these three, and I made them available for anybody to use. So this is called compaction. I compact my memory from time to time to make the unused fragmented memory available. But at the cost of CPU time, right? Operating system is going to take lots of time to do this compaction. Again, I don't like the idea of using the CPU time to do this kind of stuff. But without doing that, 1/3 of your memory will be unusable. If the memory is not unusable, then that means what? I need to keep swapping back and forth between the disk and the main memory. That will cause even more CPU inefficiency. So instead of causing swaps, maybe do the compaction from time to time. Okay? So, So I kind of looked at all of them. Okay? First fit, next fit, best fit, worst fit, and I'm going to, this one I'm going to skip. The idea is the same. Search for the available position. Search for the available position. Some people say that to keep my empty list, the whole list, this is my whole, another whole, and another whole. Don't use the useful part of the memory. Use the empty part of the memory. See, this place is empty, right? This place is empty and this place is empty, right? Nobody's using them. Why don't I use those memory locations to keep my list? That's the idea. But nobody's using them anyway. Okay? Not the process list, but the whole list. Use those areas, unused areas, to keep my whole list, and that kind of makes things a little bit more efficient. That's what I say. Keep the whole list and process list separate. Two lists. One is the process list, the other one is the whole list. Whole list can use the free memory. Okay? Okay, any questions so far? What did we say? We said that this contiguity is killing us. Okay? Let's go back here again. If A needs 5 blocks of memory space, 20 kilobytes, okay, 5 contiguous spaces, and well, do I need to keep them in the same place in a contiguous way? Can I store some of them at some other places? Or maybe if I can't do that, okay, mostly I do this. If A is my program, okay, this is my code segment, text. Again, this is code. This is data, and data. Okay? So I usually do this. Whenever I am using code inside this block, it needs some data from here. The rest of them, these 3 blocks, are not used at all. Okay? So why do I have to keep these 3 blocks in my memory? Okay? That's the idea. They say that who knows this best? Who knows that which parts of the program should be kept in the memory and what parts of it should be kept, can be kept, might be kept on the desk? Well, who knows it better than the programmer? So the programmer says that whenever I am using this part of the program, you don't have to keep this part of it on the memory. So you may keep them on the desk. Okay? So I am suggesting the operating system that you don't have to load me altogether to your memory. Keep some part of my program on the desk. So suddenly you have a very, very efficient way of using your memory. You don't have to load your whole program at the same time, but parts of it. That's called the idea of overlays. Okay. Okay. In 1960s, again, the idea appeared. Programmers split programs into little pieces, and they call them overlays. And some of them are kept on the disk. And whenever they are needed, okay, the program says that now I need this part, load it from the disk. So kind of the program itself helps the operating system which part of it should be on the memory and which part of it on the disk. So operating system uses this idea to keep many programs in the memory running at the same time. Okay, so that's the idea. And of course, to do that, the programmer has to be a very skilled programmer. They know how to do this kind of stuff. If they don't do their job right, then that's going to cause lots of problems for both for the operating system and for their programs too. Okay, and that's kind of solve the problem of if your program is too big to fit into memory. I mean, if you remember those, nowadays we don't have it anymore, but we used to have, we still have actually video programs, video games, right? That came with many disks, and while we were playing the games, the program used to ask, now insert the disk number 3, disk number 4, etc. That's because you can't fit all the data of that game program in my memory. That's too large. Okay, so that's called again overlays. If you cannot fit all the data in your memory, then you are going to divide it into overlays. And the size of the overlay and whenever they are going to be loaded will be decided by the programmer who writes the code. It says that I have 1,000 functions. I will keep the first 200 into this overlay, second 200 into this overlay. Also, I have 2 gigabytes of data I need for my program, but I am going to separate into overlays. Okay. Again, 1960s idea. It solves some of the problems, but again, we don't want to expose this kind of complexity for our programmers. That's not the idea of the operating system. The operating system says that I am going to handle these kind of problems myself. You don't worry. You write your program as if the whole program is in the memory. If they need to be loaded, I am going to load it, and I'm going to load this, do this overlay management myself, and you are going to write your program like the whole memory belongs to you. I mean, that's how we write our C programs, right? We never care about if my program will be loaded from the disk, if it is swept out. We never care about am I accessing the right part of the memory and etc. We just write our programs and we think that the whole computer belongs to us. And if we make some bad mistake, operating system just stops our program. It tells us that this program caused a segmentation fault or illegal instruction, etc. That's what we are going to do. So they have invented this virtual memory. Okay. Again, with the help of the hardware, we are going to ask more from the hardware now. Okay. Virtual memory is this. Again, each program has its own address space. Okay. Like the base and limit registers. But this time, my address space is broken into chunks like the memory blocks. It's called pages. Okay. As a programmer, I don't know that it is separated into pages, but the operating system sees it that way. Say that your program, let's say, if each page is like 4 kilobytes as before, operating system is going to say, okay, this process is going to take 10 pages and etc. Okay, I am using virtual memory, and I'm using the virtual addresses. As a program, whatever I say, okay, whenever I say that I am going to access this memory location, It's not the real physical address, it's a virtual address, okay? It is translated to the physical address by the computer hardware, the memory management unit, MMU, okay? That's called mapping. And my programs, they don't have to be contiguous anymore. They don't have to, my pages, they don't have to follow each other. They can be at the different places on the memory. That would eliminate any need for compaction, because this is not going to cause any fragmentation. And this approach will solve lots of problems, such as compaction problem. I don't need to relocate my code. My memory protection is going to be very, very easy, and many other, like the overlay automatic overlaying mechanism, they all will come with this idea of virtual memory and virtual addresses, and we are going to see it that way. Okay, that's called paging, and modern operating systems, they use paging a lot, and paging will be our main tool for satisfying our main two goals of operating system happening with the memory. Okay, so CPU, our program thinks that it is working in its own address space, but the memory management unit keeps translating my addresses to physical memory addresses all the time. So the memory management unit is going to be more complicated hardware wise, okay, and it will keep a page table to make this, to facilitate this address mapping from virtual address space to the physical address space. And as an operating system, I am responsible for managing the memory management unit. Okay, the memory management unit has tables. I am setting up those tables, and it is my responsibility, and it's a privileged responsibility. Nobody else can access to that. Can have access to that memory mapping tables and etc. And this will be the whole picture, and I'm going to show you the idea. Okay, so that will be it. Let's say I have a virtual address space of 64 kilobytes. Okay, so it is 64 2 to the 10. Okay. Am I disconnected? I think I'm back. Okay, so that's my virtual address. So my program thinks that it owns this much space, starting from address number 0 to some place. Okay, and operating system says that, okay, I am going to divide this space into pages, and each page is going to be 4 kilobytes. That means 2 to the 12. Okay, so if each page, this is the page size. How much is this? 64 2 to the 10. It is 2 to what? 2 to 64 is 5 6 16, right? Is that correct? 2 to 16. Okay, so what is the difference between them? It is 2 to the 4. So there will be 2 to the 4 pages, virtual pages in my memory. Okay. The nice thing is this: my physical memory is not that large. My physical memory is only 32 kilobytes. But as a programmer, I think that I have 64 kilobytes, and operating system says that, okay, I am going to keep some of your pages in my memory using this configuration, and some of your pages will not be in the memory. They will be kept on the disk. Okay, but I don't know that. As a programmer, I say that, okay, I have address number 0, I have address number 40K, I have address number 60K. I can do whatever I want with this virtual address space. But the operating system, okay, without telling me, it keeps this page number 0 at this location in the physical memory, page number 1 at this location in this physical memory, okay, page number, I don't know, is this 7? I don't know, page number 7 at this location in the memory, okay, and some of them are not in the memory at all. So whenever I run a program, for example, jump 20K, something like that, okay, so it should be around here. Whenever I say jump there, okay, the memory management unit on the fly translates this address, okay, to the page, to this location. So in physical memory, I am using this one, or maybe, no, I am doing it wrong, right? 20, okay. In physical memory, I am using this one, but in virtual memory, I think that I am using this location. So this memory is not, does not exist actually, this virtual memory. That's why the name is virtual. Everything is happening in the physical memory, but I live in this virtual world, which makes it much easier for me. I think that all of my pages are contiguously reside on my memory, and I can do whatever I want with this virtual memory. But on the fly, everything is translated automatically. And there is a table actually. This is my called the page table. The page table keeps these points to pointers to the physical memory. Note that, okay, there is a pointer for the whole page. So this whole 4 kilobytes actually live in here. This whole 4 kilobytes live in here. So this mapping is done for the page basis, okay, not for each byte by byte page basis. Yes.
Does the base register and limit register values are also in virtual space or in physical space?
We don't have base and limit registers anymore. Okay, it is gone. We don't. What was the problem with the base and limit registers? If my program is too big, it doesn't fit into the memory, right? This solves it. Okay, and I don't have the compaction problem anymore. Why? Because in my physical memory, I can see my program is not contiguously stored in my physical memory. Even a single block, if it is available, I can use it any way I like. Okay, my program is not contiguously stored on my physical memory anymore. Okay, I can change the orders of the pages. Okay, so how it is done, it is very easy. I mean, the nicest thing is that implementation of this idea is very easy hardware wise, and I'm going to show you how it is done, I guess, tomorrow. So this is how it is done. This is basically, you take a virtual address, okay, you take the virtual address, you take the last part, and this part will not change, but you take the first 4 significant digits, you make a table lookup from this table, and you get a value, you put it in front of this address, okay. So this part and this part is the same, and this part is translated to this part, and if you put them together, it makes your physical address. So there is no addition, there is no comparison. It is better than, it is more efficient than the base and limit register solution, and that will be basically it. Okay, so I need to keep this table in my memory management unit. That's why I need the hardware help. If I can manage this memory management unit right with the operating system, this idea will work beautifully, and it's going to solve lots of problems. No searching for the available space, no compaction. No overlay help from the programmer. lots of problems will be solved with this approach. It's called paging and virtual memory. Okay, that will be it for today. If there is no question, I will see you tomorrow morning.